So I will present two works realized with those people about maximum independent set in H3 graphs. So let's just, so we are on the same page. So independent set, I think, was already defined. So you want vertices that are pairwise non-adjacent, and you want to maximize the subset that you find. And H3 is for induced. So H3 graphs will be, you have no H as an induced subgraph. And we'll start by discussing the status of this question for the classical complexity, so for P versus NP hard. But then we'll move to the parameterized version of this question, which is if you can or not find an FPT algorithm. So what is known in the, well, maximum independent set is notably NP hard and also very hard to approximate. You cannot really do much. You cannot approximate it with this ratio, which is very close to n to the 1 minus epsilon. If P is different from NP. So you could now ask, what if I forbid some induced structure? And actually for this question, the dichotomy is probably, even though it's not settled, the result or the conjecture is very clean. So all the hard cases, they fall into this reduction by Alexeyev, which is just, the trick is just to subdivide the edges of your graph an even number of times. So here I did it just 2, but you can do it another constant even number of times. And you see that solutions, it's not difficult to see that solutions of size k in the original instances, they will correspond to solution of size k plus cm, where you subdivide 2c times the edges. You have no choices for those vertices when you took the so this is vertices that you choose in your solution. So here you will have no choices, and you will have some choice for the edge for which you have no endpoint. But you will be able just to take this amount of. So if I do this with a sufficiently large constant c, now I already know that if H contains a cycle, the prime will remain NP hard, because in those graphs there won't be small cycles anymore. If you forbid it's less explored, but you can derive some results from.
So you have to H is the cycle, and you for example you forbid C5 or
I
would say if you forbid
I would say yes, because the number of boundary classes will be infinite more or less, and then you end up with
yeah, if the graph is a cycle, yes, and also if you have k14, yes. So we'll see. You will see more results, and maybe it will answer this question in some sense. So also, maximum independent set is NP hard, remains NP hard on subcubic graphs. So now if I start from a subcubic graph, so every vertex has degree at most 3, and I do the same trick, you notice that, well, you don't have vertices of degree more than 3, and the vertices of degree 3 now they are far apart. So basically, not only you're left with only, if you want to deal with connected H, only trees, but actually only trees with at most one vertex of degree 3 and no vertices of degree more than 3. So that leaves you exactly with the current state of affair, which is the open cases here are path when H is a path, or when H is the subdivision of a claw. And actually we know up to P6-3 polynomial algorithm, so P7-3 would be the first open case. And we know for claw-free graph and also for fork-free graph, so this is a fork, a polynomial algorithm, so there will be this and this graph are the first open questions for the subdivision of a claw. So now, as I said, we will. I just want to mention one thing. So we will consider like dichotomy results. Here we will be far from settling the dichotomy. Here, at least, the statement of the dichotomy, if you believe that all those remaining cases are easy, we have a nice understanding of what's going on. There is just one dichotomy which is solved. It's Cupitas versus no Cupitas. So we have Cupitas. There is a recent result of Chudnovsky, Pilipchuk, and Tomase. So graphs without subdivisions of the claw, they admit a Cupitas, and this you could rule out it by showing that the parameter is actually APX horn. So let's go back. Let's go now to our question, which is FPT versus the W1 hard. Yes. And here, what was known before we started to work on the question, I think by Dabrowski et al., is that if H is on at most 4 vertices, there is an FPT algorithm, except they left open the case of the C4, except for C4. And there was also some other result that for K13, so when you have the claw plus 1 leaf, K13, this was W1 hard.
So when you say FPT, you mean the parameter is
the side of the solution. So we're really looking at is there some algorithm of this form, and you don't need to know about W1 hardness. Just think maybe as hard as maximum independent set in general graphs, and think of it equivalently as we cannot have such an algorithm. Yeah, you can you can assume that H is connected. You can, of course, ask the question if H is not connected, and then you're left with more open cases. But already understanding the situation for H connected would be nice. So what we did in the first paper, we first got one reduction coming with 3 slight variants. So we have 3 variants of this reduction that together told us that actually if the graph H has not this specific form, then all the primes are W1 hard. So the specific form is actually mimicking the open cases for the classical complexity. So I won't be too precise here, but it's basically what you obtain by substituting those vertices into cliques. So that would be a P4 that I substitute with cliques. And the interaction here is almost complete. I can just remove one edge at most. So same for the claw and the subdivided claw. So now those vertices are cliques, and an edge it's complete, but I can remove one edge if I want. And there is some additional technicality here for the path. I cannot force those red edges, which means that I remove one edge at most. There will be one interaction which is a bit more complicated. There will be one interaction where I only know that there is no 2K2. So that's that. And we actually, the third variant actually implies that your A should also map into the subdivision, into this thing, which is the line graph of a claw, basically. So what was interesting here is that now for this, I should first say the conjecture. So we could conjecture that we'll forget about those, the fact that I can remove at most one edge here, and we'll conjecture that if I take a path and I subdivide and I substitute every vertex into cliques, then I'm FPT. If I do the same conjecture for the subdivision of a claw, it fails for that reason, because you also have to be mappable into this line graph of a claw. And actually this, for this H, already, so you see there is this clique with one vertex, and two cliques with two vertices. Already for this pattern, it's W1 hard. So now we'll just, this was an introduction to motivate that we'll just consider the first step, which is substituting cliques into the path. Questions so far? And actually, if you care about, okay, so here in particular here we settled the case of C4, it's hard. Now if you look at, this effect didn't work to me. Vertices on, graphs on 5 vertices, those were the 4 open cases after the first paper. And you see that this one and this one, they are actually, they fall into the P4 of cliques. So I have one clique, one clique, one clique, one clique. So if we could show it for P4, we would settle this and this in particular. So again, what we, let me just go back quickly to the first paper. So in the first paper, we also settled the case of a P3 of a clique. So now the natural question is to go to P4, and we'll settle also small cases, and also have a family for which we know that the prime is FPT. Yeah.
So you're forbidding paths together with one of these graphs?
No. You're just forbidding this graph, which is obtained by a path where you substitute every vertex by a clique.
Yeah, but then you have sign already.
But they are not induced. You don't have an induced C4.
Why is it I guess.
Sorry?
That's why you forbid the 2K2 also.
No. Here you don't have C4s induced. So you just forbid this.
Ah, okay.
So if you think of triangle-free graphs, they are hard for the classical sense, but they are trivially FPT because you're forbidding a clique. So now your independent set will be small. No, it will be large. So your parameter will be large. Okay. So actually, we'll fall short of proving this. So we'll just be able to add one vertex to this path, which will be enough to settle those two cases in particular. So it seems a bit ridiculous. I mean, we're just adding a vertex. But if you think of it in the classical sense, so for P4 free graphs, so co-graphs, there is a very easy algorithm. And then there was many efforts to show it for P5 free. So we're actually kind of doing the same, but with some lag. We're going from P3 to P4. Okay. So So now we'll just try to show that there is an FPT algorithm when you forbid this, and we will start with something seemingly unrelated, which we could call co-graphs with parameterized noise. So a co-graph is a graph where you have inductively a bipartition AB, and it's either empty between them or it's complete. Or you have all the edges. So here, the parameterized noise will be of this form. We'll have a set. So the bipartition will not be very clean. We'll have a set, but its size is bounded by our parameter. And here we'll allow, actually, if it's supposed to be empty, we'll allow a vertex to have a number of neighbors which is not too big. So less than something, again, bounded by the parameter.
Only one vertex?
All the vertices here, they have at most. Yeah. And for the complete case, the same with non-degree. So all the vertices, they're non-degree. Is not too big into B. But actually it will be even more permissive here. So another kind of structure that will allow is that to generalize when it was empty between A and B, we will say that here it's K DD free. You don't have bicyclic DD. And we'll show how we can solve or Turing reduce this thing in FPT time to something where the parameter is smaller, and then we'll use it later together with this in order to settle our problem. So how does this work? So this use so it's a subgraph. I don't care what's going on here. So what I do is I first guess the amount of vertices that you take in each part, K1 and K2. And we'll see later how we deal with the case where K1 or K2 is 0. So here think of them as being strictly positive, and they sum to K. Then, because they are strictly positive, they are also strictly less than K. So we can actually call our FPT algorithm with smaller value of K. This is possible and still gives FPT running times. So we'll call it, in A, we'll ask for solutions of size k1. So we'll extract a first solution. Then we will remove this from the graph, and we will ask again for a solution. So this process will terminate at some point. And if it terminates too early, we'll be happy because we will know that the solution has to intersect what we computed so far. So we can imagine that it continues forever, forever being a large function of k. And we'll do the same here in B. We'll extract a solution, extract a solution, extract a solution, and so on. Now we have a solution of size k. If we have one solution here without any edge to another solution there. So we can assume that for each pair there is at least one edge between them. So let's call this large number S. So now look at the graph induced by the solutions here and there. So it's by hypothesis this KDD3. But you need S square. You need S square edges to spoil all the solutions. And now we will use the Covary so as to run theorem. Which is a theorem in extremal combinatorics, which says that if you're KDD3, your number of edges is smaller than D times n, number of vertices, to the 2 minus 1 over D. So here n for us is S times k1 plus k2, so it's sk. And we will fix D large enough so that S square is actually larger than this. Because here you see that the S appears with the exponent 2 minus 1 over D. So I can find a D which is long enough to have that S square is actually too big. Now, it actually also, we have to deal with the case where K1 is K, for instance, or K2 is K. But we can do the same trick. So if K2 is 0, we can repeatedly find solutions of size K minus 1 in this part, and use the same trick with single vertices in the other part. We'll reach a contradiction, or this will terminate soon enough so that we can branch on something small in K. So I won't present, we'll use this, but I won't present it. In the 5 minutes that I have left, I will try to see why it's related to what I said so far. So, so what we will do is to start. So I will skip a lot of technicalities so that we have only the interesting ideas. But we will manage to start with a collection of cliques and so on that are totally independent. There is no edge between the cliques. And we have at least 2 cliques above. And they are all of size between 3t. So what was t? So we were trying to see to show that if we don't have this graph, where this is a clique, 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 fully complete, fully complete, fully complete, then independent set is FPT. So this is this t, and something depending on t and k. So those cliques are not too small, not too big. So you notice that because they are independent, I cannot have more than k of them, otherwise I have a solution already. So I will look at how the rest of the instance sees those cliques. So it defines two layers of classes. So just a quick definition. So I will say that a vertex TC is a clique if it has more than t neighbors in the clique. So now I will partition the rest into classes, which tells me, okay, this would be the classes I, the class is pi. So I is indexed over k. So think of this. This is clique 1, clique up to potentially k. And all the vertices here, they TC exactly the same set of cliques. So I have 2 to the k at most of those classes. And within classes, I can further refine to the actual neighborhood of each vertex, because this is also bounded by 2tk square. So I'll have this further refinement. Now, for instance, if you TC 2 cliques, then I claim that you actually see all the clique here and all the clique there. So this is because every subclasses that will be small, I will put it in some kind of trash in this set R bounded by K. So you can imagine that all the subclasses are big, and big meaning greater than Ramsey of K plus 1 and something, so that I can either extract an independent set of size K plus 1, or I have a clique of large size for free. So here for free, I have in particular a clique of size T. So if you miss one vertex here, there will be a 1 T, T, T there. So you have to see everything. So now we will use those kind of tricks. Maybe I will show just one, and to actually show that the classes here, they are actually a laminar family. So they cannot overlap. So you can represent their inclusion as a tree. So you can have that this is the largest class, meaning it sees something maximal as cliques, and inside you will have things like this, or you can have things nested like this, but never you can have an overlap like that where this, and this is empty, is non-empty. And actually, to now link it to that, in the case where they are disjoint, we'll have one of the two cases that are presented here. We can re-express the graph and use this algorithm. And in this case, where one class contains all the other, we'll use the other one. So let's see just one example. So if you take, and then I conclude. So if you take two classes that are, one is included in the other, so this would be J, this would be I. So we have Pi here, Pj here. So here, the reason why it will be KDD free and we'll be able to conclude here is that if you find a large, no, sorry, here we'll have the other case. So if you have one vertex with a too large non-neighborhood, you'll be able to build this object. So this will work the same with the proper inclusion, and the disjointness will have another property, and then we'll be able to show that the overlap is impossible. Again, using Covariant-Shorström, you would have something KDD free, but something with at the same time many edges, which is not possible. Okay, so I guess I will stop there. Thank you.